All right, we're back. We're back for the second half of multiple regression, which should be class 4, I believe. So multiple regression part 2, class 4. And in the second part, we're going to go over actually running statistical analysis using SPSS. We'll use SPSS with fields data sets, and then we'll switch and we'll use SPSS with our COVID data set. So that's our plan. All right, if you remember to run in SPSS a linear regression, a simple linear regression is pretty simple, and it's the same for if we're using more than one predictor or more than one variable. We just go to SPSS, we go up to that top menu, we hit Analyze, a menu will come up, we pick Regression, and then we pick Linear, and that'll take us to our menus, and that's pretty much all we need to do. From there, we just enter our choices. All right, so again, the record sales example from field, a recap. So a record company boss was interested in predicting album sales from advertising. The data consisted of 200 different album releases. The outcome variable was sales, CDs and downloads, in the week after release. And the predictor variables, we now have 3. The 3 predictor variables are the amount spent promoting the album before release, the number of plays on the radio, and the image of the band. So band image, not brand image like I thought last time. All right, and again, if we wanted to, we could run our scatter plots. And here we have our different scatter plots with all 4 variables: album sales, advertising budget, number of plays on the radio, and band image rating. So we have all 4 of our variables. And again, now if we've done things correctly, we would be at this box or this page in SPSS. And we now are going to enter several different predictors. And we're going to enter them at different steps. So you can see here our dependent variable is album sales. We brought that over. We've already entered block 1. You can see we're on block 2. So we've already entered block 1 of the predictors, which I thought was advertising budget. It was. So advertising budget was step 1. And now we're entering number of plays on the radio and band image rating. We won't really need to use the selection variable, the case labels, or the WLS weight. And of course, then again, we have a number of selections we can make right over here. So again, we can see field selection. Field pretty much selects most everything, and he makes use of all these things. Again, we don't really have time to go through everything here in this lecture within this format, but if you go through into the book, if you look in your book, he will explain all of these. And of course, he likes to interpret and get these plots, and it's a good idea. He gets the histogram plot, the normal probability plot, and the plot of the Z residuals and the Z predicted. So the standardized residuals and the standardized predicted. And then for diagnostics, again, he likes to get a lot of diagnostics. You can see he's chosen a lot of diagnostics here, including various residuals. I actually like to get the unstandardized as well as the standardized. And so you can see a lot of his different choices here. Again, you could make your own choices. And if you want more information on what a lot of these mean, you can, again, turn to the book. Okay, so he inputs his data, he hits OK. Again, if you do this right, you go to your output, and there you see your output. You see your results. If not, if you get an error, you did something wrong, and you better go back and check what you did wrong. Okay, but we start with our model summary, and we can see here on step 1, we enter the advertising budget. That would be the same as we did for the simple regression. And so we can see our R, our R squared, our adjusted R square, the standard error of estimate, the R squared change, the F change, degrees of freedom for that F change, degrees of, well, the two, F always has degrees of freedom 1 and 2, so the 2 sets of degrees of freedom, and the significance of the F change. And again, so, the R is the overall correlation, R squared is that correlation squared. The adjusted R squared is for shrinkage. I don't really think there's much use made of that by most people. Standard error of estimate gives us a standard error around really for prediction purposes. The R squared change, which for the first model, of course, is from 0. So we're going from 0 to 0.335, so the R squared changes 0.335, and that change is highly significant with 1. Well, the F is 99.587 with 1 and 198 degrees of freedom, and the p-value associated with that is 0.000. Of course, the real interesting thing here is when we add in our second set of variables. And of course, again, this would be, he's basically here doing hierarchical regression. Okay, so we talked about hierarchical regression. He's basically doing hierarchical regression by forced entry. So he's using forced entry. His choice here was forced entry, and he's using forced entry to do hierarchical regression. Okay, so we can see when we now load in 2 more variables, and of course the constant's already in there. When we load in 2 more variables, band image rating and number of plays on radio, the R goes up quite a bit, which is good, to 0.815, which gives us an R squared of 0.665, an adjusted R squared of 0.660, standard error of estimate of 47.087. Our R squared change is really a whopping 0.330. Typically, you will not find that big of an R squared change in your analyses. And this is the F then associated with this R squared change. So this is the F change. It's 96.447. Again, well, so we have 2 and 196 degrees of freedom this time. And the significance of the F change is 0.000. All right, R and R squared. Again, R is just the correlation between the observed values of the outcome and the values predicted by the model. So basically, we use those B weights to get, for an individual case, the prediction, and then we compare it to the outcome. Of course, we do that for everyone, and we calculate a correlation, and that's the correlation between the observed values of the outcome and the values predicted by the model, and that's our R. And then R squared is just the proportion of variance accounted for by that model. So the proportion of variance in Y accounted for by the model. And then adjusted R squared is an estimate of R squared in the population or of shrinkage. Again, as I said, that's sort of a cross-validation estimate, but not too many people put faith in that as a real cross-validation estimate. You should either do an actual cross-validation, maybe do a holdout sample. Of course, you could argue bootstrapping is sort of like an ultimate holdout sample, but not too many people put too much faith in this shrinkage estimate. Of course, again, then we get an ANOVA table, just like with simple regression, except in this case we get 2, because we did 2 steps. So we get the model for the first step. We get our regression sum of squares, our residual or error sum of squares. They sum to total sum of squares. We have our total N is 200 again. So that gives us 199 total degrees of freedom to use. So we use 1 degree of freedom for the model, and we use 198 for the residual. We then divide the sum of squares by the degrees of freedom. That gives us our mean squares. Again, you could do that with a calculator if you'd like to test me out. And then we get our F ratio by simply taking the mean square for regression divided by the mean square for residual. That gives us our F ratio. You can see it's very large. Again, you can do that by hand if you'd like. And we can look it up in a table, but SPSS gives it to us. The associated p-value for that is 0.000, which would, of course, be significant at either 0.05 or 0.01 or even 0.001. Now, what gets interesting here, of course, is we're going to look at what happens when we put in our two other variables, or do our hierarchical regression. So when we put in our two other variables, we recalculate our sum of squares, we recalculate our residual sum of squares. We also have a total. Regression and residual add up to total. We have a new degrees of freedom because now we have 1, 2, 3, 4 things going into the model, and degrees of freedom here is 4 minus 1, which is 3. This is n minus 1, which is 199, and residual is the rest, 196. Again, 396 add up to 199. For the mean, so we take these sum of squares, we divide by the degrees of freedom, we get our mean squares. Here they are. Again, you can do it by calculator if you want to make sure SPSS didn't make a mistake. To get our F ratio, we divide the mean square for regression by the mean square for residual. That gives us our F ratio, in this case 129.498. And now we can take that, again, SPSS does it for us, looks it up in a table, the probability or the p-value associated with that F ratio is 0.000, which is significant, of course, at the 0.01, the 0.05, and the 0.001 levels. All right, and again, the F statistic, which we just went over, looks at whether the variance explained by the model is significantly greater than the error within the model, whether SSM is greater than SSR in Field's use of the terms. It tells us whether using the regression model is significantly better at predicting values of the outcome than simply using the mean. The mean on Y, of course. And so here's our next table. We now can estimate the model parameters. Of course, again, we're going to do this in 2 steps. In the dependent variable is album sales, as we can see here. First step, we put in advertising budget. We can see our constant's 134. Our advertising budget, the B value associated with that, which would be B1, is 0.096. We can see our standard errors for our B's, our betas, or our standardized B's, or our big B B's. In this case, it's 0.578 for advertising budget. We get our T's, which are used to determine the significance of whether the parameter is significantly different from 0 or whether the sample estimate is significantly different from 0. And in this case, again, the T for the constant is 0.000. The T for advertising budget, the p-value is 0.000. So they're both significant, so to speak. That gives us and then it gives us the lower and upper bound on those estimates. Of course, we can do this again. We'll do it again for now our second model. Now, so in our second model, we already have advertising budget in there, and we put in number of plays on the radio and the band image rating. And so when we look at this, we can see, okay, the constant's changed quite a bit. Now the constant's negative 2.6. Our advertising budget stays somewhat similar, 0.085. Number of plays on the radio, the B value is 3.367. Band image rating, the B value is 11.086. Again, that tells us how many units the Y value is going up for each increase in a unit of the independent variable. So it's telling us for each 1 unit increase in the independent variable, how much the dependent variable is going up. And then we get our betas right here, our 3 betas right here. Again, those are just standardized B values. We get our T's. You can see except for the constant where it really doesn't matter, they're all significant. As a matter of fact, they're all 0.000. And we get, again, our lower and upper bound estimates. Okay, then we get our coefficients. These are used for detecting, again, issues or problems. So we have our 0 order correlations here. 0 order with the dependent variable of album sales. We have then our partial and semi-partial correlations. And of course, these are used to look at, or are used to determine what variables to load into the regression equation, and are also used in determining the increment associated with that dependent variable. So it's giving us our partial and our part correlations. Of course, for our first model, there's no variables other than the advertising budget. So the partial and part correlation are all the same as the 0 order. Now, if we move to here, what's happening is we're adjusting or we're correcting the correlation between advertising budget and album sales for the number of plays on the radio and for the band image rating. So this is the correlation between advertising budget and album sales when we correct for number of plays on the radio and band image rating. And you can see it's actually a little bit higher. It's actually a little bit higher. This is the correlation when we correct just the X variable for the contribution of the other X variables. It's basically taking the residual of the X variable and looking to what extent it correlates with the Y variable. So you can see that this one's going to go down. And again, so this would be the correlation of the advertising budget with album sales once you control for the contribution of number of plays on the radio and band image rating. Or I guess a better word would be once you control their level. So once you control their level. And same thing for number of plays on the radio, you're holding constant advertising budget and band image rating. For band image rating, you're holding constant number of plays on the radio and the advertising budget. And then you have some collinearity statistics. Again, you can see these really aren't even close to the values that Field says would be problematic. Okay. And then in terms of interpreting these model parameters, especially the B values, a B value is simply a change or the change in the outcome associated with a unit change in the predictor. So it's telling us if we change the predictor 1 unit, how much of a change will there be in the variable we're predicting, the dependent variable or the outcome or the Y variable. And of course, we have to add the caveat to that, that's controlling or holding constant the other dependent variables in the model. All right? So that's your B value. That's your little b value. Now your beta value is a standardized B value. It tells us the same thing, but it's expressed as standard deviations. So don't take this slide the wrong way. Field is not saying that your beta is a standard deviation measure, because it's not. He's saying that a 1 standard deviation change in X will lead to a beta unit change in the outcome variable. So the beta is in standard deviations the amount of change that will occur in the outcome variable, or Y, or the dependent variable, by changing one of the X's 1 unit. Again, given that you've held constant all the other x's in the model. Okay? Hopefully you follow that. So, for example, our B for advertising budget in this case was 0.085. So that means as advertising budget increases by 1 unit, album sales increase by 0.085 units. Since both variables were measured in thousands, therefore for every $1,000 spent, 1,000 in America, more spent on advertising, an extra 0.085 thousand albums, or 85 albums, are sold. This interpretation is true again only if the effects of band image and airplay are held constant. Similarly, for airplay, our B is 3.367. Now again, you can't say because that's larger than advertising budget, airplay is more important than advertising budget, because airplay is measured in different units. That's one advantage of the betas, the big B betas, is that you can make more of a conclusion about importance, although you still have to be careful there. So, for airplay, as the number of plays on the radio in the week before release increases by one, album sales increase by 3.367 units. Every additional play of a song on the radio in the week before release is associated with an extra 3.367 thousand albums, 3,367 albums being sold. Again, this interpretation is true only if the effects of the band's image and advertising budget are held constant. And then there's the band image. If a band can increase their image rating by, okay, well, I should say what the B value is first. So again, the B value for image was 11.086. If a band can increase their image rating by 1 unit, they can expect additional album sales of 11.086 units. Every unit increase in the band's image rating is associated with an extra 11.086 thousand albums, or 11,086 albums being sold. So again, though, that interpretation is only true if we hold the effects of airplay and advertising constant. Okay, so that's how we can interpret those B's in the equation. All right, we're now looking at the interpretation of betas. Again, the interpretation is very similar. So for advertising budget, our beta, our big B beta, was 0.511. So as the advertising budget increases by 1 standard deviation, album sales increase by 0.511 standard deviations. Again, all of these are going to be when you hold the other variables constant. For airplay, the beta is 0.512. So for airplay, as the number of plays on the radio in the week before release increases by 1 standard deviation, album sales increase by 0.512 standard deviations. And finally, for image, the beta is 0.192. So a band rated 1 standard deviation higher on the image scale can expect additional album sales of 0.192 standard deviation units. And of course, here Fields converted that into, that would mean 15,490 sales, and it would mean a 1.40 unit increase on the image scale. And again, all these are holding the other variables constant. And then we have our collinearity statistics. We've highlighted those right here. You can see again, there doesn't really seem to be any issue with collinearity. Here's the predictions. Here's the homoskedasticity results, the plots. Again, if you want more information on this, go ahead and go to Fields' book. Here's a plot of the regression standardized residuals. You can see they look pretty normal. And if we look at the PP plot, it looks pretty normal as well. And then, which I think is very helpful, Field shows you how you can report this model in a table. He recommends giving each step 1 and step 2, giving the B values, the standard errors of the B values, the betas, and then the associated P's. And then below the table, he gives the R-squares and the changes in R-squares. You'd probably see a lot of people who actually include those or work them into the table, but that's how Field does it. At this point, we're going to return to analyzing our data, our COVID data. Again, we have COVID data for 50 states, and we've eliminated now District of Columbia. You'll see the dependent variable I'm using here is deaths per 100,000. So the dependent variables deaths per 100,000. And I'm going to start off by just putting everything in at once. So I'm going to enter my three independent variables. Of course, also I have the constant. So I'm going to enter my 4 variables to try to predict deaths per 100,000 from COVID. And the 4 variables would be the constant, the density per square mile, the number of individuals identifying as Black per 100,000, and the number of nursing beds per 100,000 people. And again, if you go back to the last lecture, I explained why I came up with those variables, and those were some of the variables that did correlate with deaths per 100,000 from COVID at the state level. So when we look at this, we can now see that when we put all 3 in, first we get our unstandardized coefficients, or our B's. The constant is 21.686. Density per mile, the B is 0.074. The number of individuals identifying as Black per 100,000, the B is 0.001. And the nursing beds per 100,000, the B is 0.081. And here we have the standard errors. And again, you can't really compare these B's because, the meaning sort of units within each of these 3 independent variables is different. For importance, it's a little bit easier to look at the betas. So here's the betas. And so you can see in terms of our standardized coefficient or betas, density per mile has a beta of 0.438. The number of Blacks per 100,000 has a beta of 0.223. And the number of nursing beds per 100,000 has a beta of 0.390. Here's the associated T's. And here's our significance values. So you can see that the constant isn't significant. Again, that does not matter. But if you, to the extent you can put faith in this data, you can say that those individuals who argue that one of the things contributing to COVID is the density of the population, or the more people you have packed in together, the more COVID deaths you're going to have. There's some evidence for that. The p-value associated with density per mile is 0.000. And for those who argue that we have problems with our healthcare system and other general problems in society that contribute to more deaths for those who are minorities in our population from COVID, there is some evidence for that. Again, for our coding of individuals identifying as Black per 100,000 within the population, or population of the state, it is significant, and the p-value associated with is 0.043. And if you think part of the problem is, hey, the more nursing homes you're going to have in a state, the more deaths you're going to have. There is some evidence for that because again, this is nursing beds per 100,000, and we can see the p-value is 0.001. So actually, in this case, all three of our predictors are significant. And again, these are significant even after controlling for or holding constant the other independent variables. If we move forward, now what I've done instead is a stepwise regression. So, we talked about stepwise regression. Here, I've done a stepwise regression. And you can see what SPSS does. It's going to enter in the most highly correlated variable at each step. So it goes through and it says, well, at step 1, the most highly correlated variable is density per mile. And you can see that that does result in a significant F change. And it increases the R-squared 0.297. Of course, that's compared to initial R-squared of 0. You can see when we add in nursing beds per 100,000, the R-squared is 0.147. Again, that's a significant R-squared change. And when we use or add in as a dependent variable or as a predictor, the percentage of individuals identifying as Black in the population, it's actually the number of individuals identifying as Black per 100,000, then we see that our R-squared change is 0.048, and that's still significant. That's still a significant R-squared change. So again, it suggests that all three of these variables are important in predicting deaths from COVID. Now again, we don't want to overinterpret this because it's at the state level. I mean, I find this, I find this interesting, but it's easy to overinterpret it. You probably have to be careful about the interpretations you're making because we're looking at state level data. And here's the coefficients from the stepwise analysis. So you can see again, step 1, we just have density per mile in the regression. And here's our B and our beta and really all the data. Step 2, SPSS brings in the nursing beds per 100,000. And there's our B and our beta. And then step 3, SPSS says, well, we can still bring in one more variable. And that one more variable in this case is our coding of individuals who identify as African American within the state, actually per 100,000. And so that variable is still significant. And here's our B value, and here's our beta, and our significance level. So you can see for the stepwise, it's going through 3 steps. Now, in this case, we don't have a fourth variable. If there was a fourth variable and it didn't result in a significant R-squared change, then SPSS would not add it. The fourth variable would not be added in to this stepwise regression. Okay, then finally, I've done a hierarchical entering, similar to what Field did. You can see I started with just, again, the dependent variables, deaths per 100,000 from COVID. The predictors are going to be the constant and density per mile. So that went in at step 1. At step 2, it's cut off, unfortunately. But at step 2 of the model, then we're putting in the other 2 variables. So at step 2 of this model, we're putting in the other 2 variables. And again, you can see, of course, the sum of squares, the degrees of freedom, the mean squares. The F ratios, again, are simply the mean square for regression divided by the mean square residual. And then in both cases, it's significant, 0.000. The models are significant in both cases. And that's with here the hierarchical entering. This is now the R-squared change again for the 2 models. So you can see, again, this is with hierarchical entry. So the first step was just to enter the constant and density per mile in predicting deaths per 100,000. And you can see that again, the R was 0.45, the R squared 0.297, standard error estimate, the R squared change. Again, that's going to be equal to R in this case, equal to R squared in this case because you're starting from 0. The F for the change, the degrees of freedom for that F for change, and the associated p-value. Now again, for model 2, we put in 2 additional variables. Our nursing beds per 100,000 and our number of individuals identifying as Black per 100,000. And when we put those 2 in, we again find the R increases, as does the R squared. Actually, the R squared increase is a 0.195 increase, which has an F value associated with it of 8.838. And the change in F is significant. And this just shows us then for that hierarchical model, the associated coefficients. So this shows us the associated B values, the associated beta values for this model. And you can see we also have, it also of course gives us the confidence intervals, the correlations, both the zero order partial and part, and the collinearity statistics. And we can see that really there doesn't seem again to be any problem in terms of collinearity. With stepwise, again, if this was not stepwise, this was hierarchical. But if we were doing stepwise, again, stepwise relies upon these partial or semi-partial correlations to choose the next variable. So again, what stepwise would do is after the first step, it would look at what's the highest remaining variable in terms of its partial correlation, and it would bring that next into the stepwise regression. There is also something called robust regression. Field mentions this. I went ahead and ran the robust regression, and you can see the results here. And I don't know, they're probably not all that much different from our other results. But you can, if you want, you can try running robust regression in SPSS. I just decided to run it, and I threw the results up here. Control variables. Field doesn't really discuss control variables. I gave you a lot of readings on control variables. A lot of people in sociology use a lot of control variables. In social psychology, you see a lot of people using control variables. In psychology, you see people using control variables, maybe not as many as in sociology or social psychology. I myself have a lot of problems with control variables, and that's why I gave you those articles. My problems include, one, the more control variables you put in, the more sample size you're really using up, the more unstable you're making your model. The second problem I have with control variables is a lot of times I think it's sort of just a cop-out. If it's really an important variable, shouldn't it be in your model? So to me, a lot of times when I look at control variables, I think, well, this variable should really be in the model. My third problem, and I think I mentioned Ralph Alexander before, one of my mentors and statistics teachers. Ralph would always say his problem with control variables is that he doesn't know what a variable means after you control for the control variable. And I think that's especially true when you're using non-demographic control variables. So I have less problem with the use of demographic control variables. I can understand why people use them, especially if they have trouble recruiting the numbers they want from various groups. But I have a lot more problem when you're controlling for variables that are very similar to each other. For example, if you're controlling for job satisfaction and your independent variable, or the variable you're looking at, is job engagement, those variables are so similar that if you're controlling job engagement for job satisfaction, I'm not sure what you have left. And that was Ralph Alexander's problem. Ralph Alexander would say, well, after you've controlled a variable for another variable, what's the name or what's the construct validity of that variable you have left? So I gave you a lot of readings on control variables. I myself have a lot of problems with the use of control variables. I think we overuse them. I think they should be limited to demographic variables that make sense. And I think they're vastly overused. But we can discuss this in the discussion section after you've done your readings. Okay, again, if you have any questions, anything you want to debate, anything you want to ask about, you can contact me at dennisdoverspike@gmail.com. And that's the end of this part 2, and that's the end of our discussion of multiple regression. Thank you very much.